Let's do a couple more examples of solving definite integrals. We did the first couple in class, but it says evaluate the following definite integrals, aka integrate. So sometimes just the verb integrate just means solving a definite integral. And it says to practice the notation. And also for each one of these, it's helpful to think about what the graph of this will look like. Because, as we talked about in class and in the last video, definite integrals always solve the area underneath the curve over the particular interval. So with this function, we have e to the x integrated from 10 to 20 with respect to x. And if we think about the graph of e to the x and what that looks like, it's an exponential function, an exponential growth function. So over time, it will get, as we move to the right, it will get very, very large. And if we think about integrating from 10 to 20, it'll have a shape sort of like that. And actually, e to the 10th power is going to be a really, really big number because that's 2.7 is the base. To the 10th power means multiplied by itself 10 times. So this should be, pretty big, pretty large number. And same with the 20th power. And finding the area of these curves, basically I'm expecting this to be a very, very large number. But again, let's go ahead and do it using the calculus. So again, first thing we need to know is, what's the antiderivative of e to the x? But if you remember, e to the x is the only function who both its derivative and its antiderivative are exactly the same. So in a calculus sense, it's very, very easy, very convenient, because the antiderivative is just e to the x. Because again, the derivative of e to the x is e to the x, so is its antiderivative. And so nothing changes. So the area under this curve will actually be equal to the value of the function at each point in time. Just like its slope is equal to its value as well. It's the only function that has such properties. Which is why it's quite important. Anyway, so if we plug into here, we would have e to the 20th minus e to the 10th. Because again, that's exactly what this means. Plug it in, subtract, plug it in. And we could factor out e to the 10th here. Remember that this won't make e to the 10th because these are exponentials, not, you can't combine them in such a way. But you could factor and so forth. Or, of course, we could do an approximation with the calculator. E to the 20th minus e to the 10th, which is a really, really large number. But it's probably okay to just leave it as an exact answer, or even factor it if we were, instead of doing it this way. Actually, another thing I wanted to show you how to do is to actually solve integrals with your calculator. Your calculator cannot do indefinite integrals, meaning it can't do an algebraic antiderivative. Well, depending on the calculator you're using. Some calculators can actually. But TI-83s and 84s, most graphing calculators can actually do definite integrals. So like, for example, the example I did in the last video, let me show you how you could do this with a calculator. But basically, within the math menu, I believe is where it's at, you can find the integral command. Function int is the function integration calculation. And if you hit enter, it will actually create a little definite integral symbol here. So say we wanted to know, what's the antiderivative or the integral of 10x minus x squared from 0 to 5. We could do so. And, you just need to fill in the gap. So plug in your function on the inside, tell it what with respect to what we're integrating, and then obviously the boundaries of integration, a and b. And then once we get all that in there, we can evaluate, and it gives us 83.3, which is not what we got. Oh, it's because I typed it in wrong. It should be minus 2x squared. So I messed that up. And that would give us 41.6, repeating, yeah, exactly what we got before. So anyways, you can check yourself. Obviously on exams, I'm going to want you to show your work as always. So using your calculator is fine, but you still need to know how to do it and show your steps. Now let's look at one more, the next definite integral from our packet. So this one, it says the antiderivative or the integral of 1 over x dx from 4 to 32. And so 1 over x is a rational function whose graph looks something like this, the reciprocal function. And we want to know, from 4 to 32. But basically, At 4, it will be 1/4, and 32 would be 1/32. So it's I'm expecting a pretty small number here because these are all fractions, and it's the height of this interval is, at the very maximum 1/4 at that particular position on 1/x. It'll only get smaller as it moves to the right. But again, if I want to solve this, I need to first know, well, what is the antiderivative of 1/x? And then I'll evaluate that from 4 for 32. But if you remember, 1/x, you can't use the power rule on. It's the one specific variant of x that will not work with adding 1 and dropping reciprocal. But specifically, it's the natural log. So the way I remember it is, since it doesn't work with the power rule, it has a special antiderivative, the natural log of the absolute value of x, which again, you can look up on our table or our formulas. But as we derived in chapter 2, the derivative of ln over x is 1/x, which is why the antiderivative of 1/x is ln, because this is its derivative and so on. And actually, the absolute value is not necessary here because both my values of x are positive. But, if you're evaluating on negatives, that's when you need the absolute value. Excuse me. So plugging these in, this would give me the natural log of 32 minus the natural log of 4. And if you recall, logarithms have a particular principle that if you're subtracting 2 different logarithms with the same base, this will turn into a division of the 2 inputs of the function on the inside. So this is actually equal to the natural log of 32/4. Which actually is divisible and even would simplify because 32 is 4 times 8. So that should just be 8, assuming I'm doing this in my head correctly, yes. And, this would give me the exact area under the curve over that particular region. Or again, of course, we could approximate that using a calculator, or even if you did not use the log law in order to simplify this answer. But if we did not simplify, it'd be about approximately 2.08 as the approximation to the exact area of the curve. Or, of course, we could use our calculator to get an approximation as well, just to double check ourselves. So 4 to 32 of the 1 divided by x with respect to x, and that gives us about 2.08, the exact same answer.